Welcome back. We're continuing in chapter 23 on electrostatic energy and capacitors. This video will cover section 3, using capacitors, and section 4, energy in the electric field. For section 23.3, using capacitors, in the previous video you learned the equation that the capacitance of a capacitor is equal to the permittivity constant times the area of the plates divided by the distance between the areas. And so we can change the capacitance by altering the area and the distance between them. If we want a greater capacitance, we can either increase the area of the plates or we can make plates with a smaller distance between them. Usually in capacitors, there's not an empty space in between, but rather there's a non-conducting material called a dielectric that stores charge and increases capacitance. As it says on the screen, dielectrics, when placed between charged capacitor plates, become polarized, reducing the voltage across the plates and increasing the capacitance. So you see the picture here, and now we've got this material in there. Now the capacitor might have a variety of dielectric materials. It could be Teflon, it could be aluminum oxide, it could be glass. But whatever it is, it's a material that is polarized. So you can see it right in there. And here's the effect of the dielectric's alignment of dipoles. So you can see here on the left is without a dielectric, you've got the electric field that goes straight from positive to negative. But you put these polarized molecules in and they will turn. So the positives will turn towards the negative on the plate. The negative side of the dielectric material will turn to face the positive plate. And what you get is additional electric field added. So you can see what I've done in the pink, the electric field coming from each of these dipoles. Now notice those dipoles' electric fields, they go against the electric field of the plates by the superposition principle. And so what we get is a decrease in the electric field. It reduces the electric field. And therefore it reduces the potential difference or the voltage between the plates. So what we get is a new electric field that can be calculated by, and here I've got the electric field with a sub-zero, so think of that as the original electric field, what the electric field would be without a dielectric constant, but then divided by this is the Greek letter kappa that looks like a K. It's called the dielectric constant, which is specific to the type of material that's being used. And if that is true, then we also get the voltage difference is the original voltage, what it would be without the dielectric, divided by the dielectric constant. Now, capacitance, remember, is charge on one of the plates divided by the voltage difference, but now we're replacing V with V naught over kappa. So dividing by kappa, we move kappa out to the side, and it becomes kappa times Q over V naught. Well, let's replace Q over V naught with C naught, the original capacitance. And so what this ends up being is there's the capacitance that, remember, is determined by the area divided by the distance between the plates, but now it's being multiplied by something, and that something is always going to be a number greater than 1. So the effect of having a dielectric in the middle between the plates is to have a larger capacitance. So practically speaking, it gives us more flexibility. We need a capacitor, we need a certain capacitance, but we might be limited by what area we can make the plates or what distance we can make them. Well, here's another variable we can add in there. Putting something in between the plates gives us, again, more flexibility in what capacitance we can design. And there's the picture again. You have the plate area and the plate separation, D, and those certainly determine the capacitance, but then you add in a dielectric and that will affect it as well. Down below you see two pictures. On the bottom is just a standard parallel plate capacitor hooked up to a battery. So hooked up to the positive terminal, we have a positive plate. Hooked up to the negative terminal, we have a negative plate. But practically speaking, many capacitors are not actually parallel plates. Mathematically, they will function that way, but physically, engineers have gotten a bit creative and inventive in designing different kinds of capacitors. So here's a standard capacitor. You have an insulating material that's the dielectric, and then these, what in the picture on the left are plates, something more flexible, like maybe aluminum foil rolled up. And so we have these cylindrical capacitors. Mathematically, it works the same because those rolled up plates, they still have an overall surface area, and they are still separated by some distance. So here's our equation that capacitance is the original capacitance times the dielectric constant. And you know that capacitance for just a straight plane parallel plate capacitor is epsilon naught times area divided by distance. So here it is, the capacitance with a dielectric is kappa times epsilon naught times area divided by distance. Usually kappa is something between about 2 and 10. That's usually. You can see air, and here is the table from the book. Air is 1.0006, which means if there's just air in between them, effectively speaking, it's really no dielectric constant at all. It's close enough to 1. Paper is 3.5, and you can see the various ones down in the chart. Tantalum oxide, 26. So that's a pretty high one, and that's one that's used in computers. The third column in this table, the breakdown field, megavolts per meter, we'll get to that. Notice also dielectric constant doesn't have any units to it. It's just a unitless factor that's multiplied by the capacitance. Now regarding that third column in the table, the breakdown field, let's talk about the capacitor's working voltage. And it's the maximum safe potential difference for a capacitor. So you can only put so much voltage to it before it will break down, and it'll probably blow up, pop, and start smoking. For a given dielectric material, the breakdown occurs at some electric field strength. Now, for example, you can see in the table it says air has a breakdown field of 3 megavolts per meter. That means that if you have a very large charge buildup and it's a 3 million volt difference, air acts as a very good insulator. However, if that 3 million volt difference between positive and negative is set up and it's over less than a meter distance, then it's just as an insulator going to break down. And that's where you get lightning from. That's where you get sparks. So air will jump over or if there is a voltage difference of 3 million volts, it will jump over a meter. And I think that comes out to be something like 70,000 volts per inch. So if a spark were to jump 1 inch through the air, then that means that there was at least about a 70,000 volt difference in charge buildup. So we can decrease the distance between the plates to get a high capacitance, and you can have less potential difference than allowed. So what if you need a high capacitance, which means maybe decrease the distance, and you need a high working voltage? Because again, the closer the voltage difference, the closer the distance, the less voltage difference is allowed. Well, you can increase the area. That'll give you a higher capacitance. You can also increase kappa, the dielectric constant. That'll get you a higher capacitance. So engineers who use electronics, maybe computer engineering, any kind of electronics engineering, are often limited in space because we like to make our electronic components smaller and smaller to fit into tighter spaces. And so they have to work with this trade-off between, we want a high capacitance, we're limited maybe between the distance between the plates, the area, the size we can make them, the dielectric constant to use. And there'll be an example coming up about these trade-offs. So let's look at it. This is example 23.2 in the book. It says 100 microfarad capacitor has a working voltage of 20 volts. That means that's as high a voltage as you're allowed to put through it. While a 1 microfarad capacitor is rated at 300 volts. Which can store more charge? Which can store more energy? And I just want you to look at these pictures. Here are two typical capacitors. I actually pulled these off, I think the Amazon.com webpage. But you notice right here, it's written in small print, 100 microfarads. Now this one in particular, not matching the example, but it says 35 volts, meaning that's the working voltage. And this one on the right, it says 1 microfarad, and it has a working voltage of 50 volts. All right, but getting back to the problem, these two types of capacitors, which one can store more charge, which one more energy? So let's get these in MKS units, get rid of those micro prefixes. Capacitor A, the first one, 100 microfarads, that's 10 to the negative 4 farads. And it has a working voltage, we'll say VA of 20 volts. Capacitor B is 10 to the negative 6 farads. And VB is 300 volts. So if we want to know what is the charge that each one can hold, maximum charge, we just do charge is capacitance times voltage. And earlier you had the equation that capacitance is Q over V, so now Q is C times V. So for the first capacitor, we get 2 times 10 to the negative 3 coulombs. For the other capacitor, 10 to the negative 6 farads times 300 volts, we get 3 times 10 to the negative 4 coulombs. So capacitor A can hold the higher charge. But what about which one can store more energy? Well, the energy, again from previous video, the energy of a capacitor is 1/2 capacitance times voltage squared. And so if it's got a capacitance, if the first one has a capacitance of 10 to the negative 4 farads, and it can handle as much as 20 volts, then we'll multiply 10 to the negative 4 farads times 20 volts squared, and we get 0.02 joules. Now, the other capacitor, capacitor B, it has much less capacitance, but it can handle much more voltage. Plus, when we're calculating energy, voltage gets squared. So the energy for capacitor B is 1/2 capacitance times voltage squared, comes out to be 0.045 joules. So capacitor B can hold more energy. I want to look now at how we connect capacitors. And there are two ways to connect capacitors together. And the picture at the top is connecting them in parallel. And the picture at the bottom is connecting them in series. And conceptually, you can see if a current is running through this, the current gets down here to a juncture, or a junction, either way you call it. And then it'll split up. Some will go to the left, some will go to the right, and then those currents will join up again and continue. Think of it like water going through pipes. The pipe splits up and continues going through. Whereas if they're in series, all of the, again, think about water pipes. All of the water that goes through the pipe goes through the first one, and it also goes through the second one. Well, more precisely defined, with parallel capacitors, both capacitors have the same potential difference, V, across the plates. So that's a key definition to keep in mind. They both have the same voltage across their plates. We might, if we continue this drawing, have a 9-volt battery here. And so on the top plate, maybe we'll call those the positive plates, it would be plus 9 volts. And on the bottom plates would be 0 volts. But they both have the same voltage difference. With series, the key definition to keep in mind is the sum of the potential differences across each is the potential difference applied to the combination. So again, let's say that if I were to continue this series drawing and it's connected to a 9-volt battery, then it's a 9-volt drop from the top to the bottom. And maybe for the first one, it's a 5-volt drop. And for the second one, it's a 4-volt drop. They will add up to 9 volts. I want to now think about what is the equivalent capacitance of the parallel setup. So often we'll find ourselves needing a certain capacitance in a circuit, but we don't have a particular capacitor that's exactly that capacitance. Well, we can combine them either in parallel or series so that mathematically they add up to give us the capacitance we want. So the formula for capacitors in parallel is at the bottom of the page right here, but I'm going to go through the derivation. Remember that capacitance of a capacitor is the charge divided by the voltage. So the equivalent capacitance, I wrote there a C with a little EQ, the equivalent, or we could say the total capacitance of these two in parallel is the total charge divided by the voltage that they have in common, because remember the precise definition of parallel capacitors is that they have the same voltage. Now, when I say parallel capacitors, I should say capacitors in parallel, so don't confuse that with parallel plate capacitors. For this discussion, we're no longer concerned about the inner details of the capacitor. We're now talking about capacitors that are arranged in parallel to each other. Let's think about the charge on each capacitor. Let Q1 be C1 times V, and Q2 is C2 times V. Now we don't need to say V1 and V2 because by definition of parallel capacitors, they both have the same voltage difference across them. Now Q is equal to Q1 plus Q2. So there's some charge on the first plate, some charge on the second plate. The total charge is them added together, and that is C1V plus C2V. Now we can say that if the equivalent capacitance, you look up towards the top of the screen, it's total charge over the common voltage, so is Q over V. Let's call that Q1 plus Q2 over V. Let's call that C1V plus C2V over V. You can divide out V and you just get C1 plus C2. So in the end, here's the main formula that you're going to need. When you have many capacitors and they're all in parallel, then the equivalent capacitance is the sum of all the capacitors. So C1 plus C2, and if there's more, you can say plus C3 plus C4. So a simple example, here's a picture. Circuit diagram, you've got 12 volts in between points A and B. Maybe it's supplied by a battery. Here's the current, and you can see the current, some of it splits off and goes down the first branch, some goes down the second branch, some goes down the third branch, and eventually they recombine and make their way to B. And in a later chapter, we'll talk more about the current and how it branches off. But for right now, we'll just look at the capacitors. They're in parallel, so the total capacitance, or the equivalent capacitance, is C1 plus C2 plus C3. Very easy calculation. 0.1 microfarads plus 0.2 plus 0.3. So we get a total capacitance of 0.6 microfarads. It's as if we could pull out all three of these and just replace them with simply one 0.6 microfarad capacitor, and it would do the same job. One little bit of notation to keep in mind, if you look at the diagram, it doesn't have the micro sign, that Greek letter mu, but it has the letter U. And often you'll see that in textbooks and on the internet, and that's often when they didn't have the ability to use Greek letter fonts. So the letter U looks kind of like the Greek letter mu, so sometimes you'll see that written. By the way, in pharmaceuticals, in drugs, when they talk about micrograms, they'll often use in pharmaceuticals, they won't use the Greek letter mu, but they'll use the letters MC. So a microgram might be written as MCG. And again, that's usually in pharmaceuticals. But so if you ever see that U, now you know what that prefix means. It's really the letter mu. Now let's talk about connecting capacitors in series. Here you have a picture hooked to a battery. I've got two capacitors in series, and I want you to look at these charges. On this plate, the plates of C1, you have plus Q and minus Q, and a capacitor will always have equal and opposite charges on the plates. And then you've got the same plus Q and minus Q. So when capacitors are in series, they've got the same charges on them. Same charge, but they have different voltages. So we can say that the voltage drop, or the voltage difference across the plates of capacitor 1 are Q over C1. The voltage drop across capacitor 2 is Q over C2. The voltage for the series is V1 plus V2, which is Q over C1 plus Q over C2. And by the way, I want to show you, when I zoom in on this picture, just to show, you've got plus Q and minus Q and plus Q and minus Q. I zoom in, separating with my green line here, the negative plate here and the positive plate here. And I want you to see that it's an isolated net charge of Q equals 0. And so this kind of leads to why they will always have the same charge, because just to make this have a net charge of 0. Now, let's go back to our equation. Let's divide the entire equation by Q. So we have V divided by Q is 1 over C1 plus 1 over C2. And V over Q, remember that is 1 over C. So 1 over the total capacitance is 1 over C1 plus 1 over C2. So we've got this addition of the reciprocals. 1 over C is 1 over C1 plus 1 over C2, and if there's a third capacitor, plus 1 over C3, etc. So this at the bottom of the screen is your main formula you're going to use for capacitors in series. Now, if you just have two capacitors in series, taking that formula at the top without the dot, 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 you can do just a little bit of algebra, combining those two fractions that are being added, and find that, here's a simplification, that two capacitors in series become C1, C2 over C1 plus C2, and that comes from about 1 or 2 lines of algebra combining those fractions. You'll notice, if you actually plug in numbers, that the total capacitance is going to be less than the individual capacitors. So remember, with capacitors in parallel, they add together. So putting capacitors in parallel is a way of increasing capacitance. On the previous example, we had 0.1, 0.2, and 0.3 microfarads, and it was a way of increasing. They added up to 0.6. But here, because we're adding the reciprocals, when you add capacitors in series, the total capacitance will always be less than any of the individual capacitances. And if you don't believe that, you can try different numbers, and as you do different examples in the book, you'll see that that's the way it works out. So it's a way of actually getting a capacitance that is less than any capacitors that you happen to have on hand. So for example, two 10 microfarad capacitors with a working voltage of 15 volts. And remember, that means that's the maximum voltage you can hook them up to without them exploding. Calculate the capacitances and working voltages of parallel and series. So let's first work with them in parallel. You have the total capacitance, C1 plus C2, and here's the picture I've drawn right there. They're both 10 microfarads, and 10 plus 10 is 20 microfarads. Now each capacitor, if they're in parallel, has the same voltage. So it's a 15 voltage difference. That's the maximum you can put up to it. And so 15 volts is the maximum you can do. And that's equivalent to my picture on the right. You can pretend that rather than having two 10 microfarad capacitors, you've just got a single 20 microfarad. And it has a voltage across it of still 15 volts. But now let's put them in series. In series, we'll use that simplified equation. C1, C2 divided by C1 plus C2. You do the math, 10 microfarads times 10 microfarads over 10 microfarads plus 10 microfarads. Let's pay attention to what the units are doing, so we don't have to go to MKS units and just say farads, but be mindful of the units. It's 10 times 10 in the numerator, 100 microfarads. Divide by 20 microfarads. And you see 1 power of microfarads goes away, and we're left with 5 microfarads. So 10 times 10 over 10 plus 10. And we can just recognize, since we were using microfarads, the units stay in microfarads. But the total capacitance, what we get is 5 microfarads. We've just put two 10 microfarads together, and we've got 5 microfarads. But now let's think about how this changes our working voltage. Each capacitor has half the applied voltage, so you can apply a 30 volt difference across the combination. Because this one up top, it can handle 15 volts, and this one can handle 15 volts. Meaning that together you can apply 30 volts, and each one will only get a voltage difference of 15. So you can actually get a higher working voltage, which then can affect how much energy we can store in this combination. Let's look now at example 23.3 on equivalent capacitance. It says find the equivalent capacitance of the combination shown. If the maximum voltage to be applied between points A and B is 100 volts, what should be the working voltage of C1? All right, so there's really two separate problems going on. One is dealing with the equivalent capacitance, and the other is dealing with voltages. Now this picture is a bit more complicated, and you might be wondering, is that series or is it parallel? Well, it's both. You see that the two on the bottom, capacitor 2 and capacitor 3, are in parallel with each other, and they will mathematically obey the rules of parallel capacitors. What we're going to do is we're going to combine them and pretend that they're one equivalent capacitance, right where my red marker is. Then we're going to say that that capacitor, it's a fictitious capacitor that we're going to mentally replace these two with. I'm going to call it capacitor 2,3 because it's a combination of 2 and 3. Well, capacitor 2,3 is in series with C1. All right, so there's the picture up at the top. So what we're going to do to find the equivalent capacitance is first combine 2 and 3, recognizing that they're in parallel. And to combine parallel capacitors, we just add them together. So C2 plus C3, 3 microfarads plus 1 microfarad is 4 microfarads. Now look at my new picture down and to the left. I am pretending that those two capacitors are now one capacitor that I'm calling C23, and it's 4 microfarads. Now I'm going to consider that I have two capacitors that are in series with each other. So I'm no longer going to think about capacitor 2 and capacitor 3 separately. They are now an imaginary capacitor 2,3. It's in series with capacitor 1. And so we think, how do we add capacitors in series? Well, when there's two of them, we can use this equation. And so we're going to do 12 times 4 over 12 plus 4. So 12 times 4, 48, over 12 plus 4, 16, and it gives us 3 microfarads. And now you look at the final picture that I've drawn. All three capacitors are such that they have an equivalent capacitance of 3 microfarads. And if you went to the circuit and you pulled out all these capacitors, you could replace them with a single 3 microfarad capacitor. So there are the pictures again, the original picture on the left, and here is the parallel capacitors combined. Now what I want to do is calculate the working voltage for capacitor 1. Well, the charge on capacitor, the charge on 1, 2, 3, that was the, I don't have the picture here, but when I combined them all into one capacitor, the charge on it is the equivalent capacitance that we got on the previous page times the voltage of the entire circuit, the voltage between A and B. Remember that capacitors in series have the same charge. So the charge of 1, 2, 3, which is, imagine this whole thing right here where my marker is being a capacitor, is the same as the charge on just capacitor 1. And so we can say V1 is Q1 over C1. Now, since the voltage between A and B is 100 volts, is across the entire capacitance, we can say Q1, 2, 3, our one our one final capacitor, is the equivalent capacitance times the voltage that's across it. And on the previous page, we got an equivalent capacitance of 3 microfarads times 100 volts, so it's 3 microcoulombs. That's the charge on our entire, our collective capacitor. And if that's the charge on the collective capacitor, then that's also the charge on on this capacitor right here, so 300 microcoulombs. And then we can figure out the working voltage by saying V1 is Q1 over C1. So 300 microcoulombs divided by 12 microfarads, and that's 25 volts. So that's the working voltage for C1. Next, we're going to look at section 23.4, energy in the electric field. Now, if you look at this capacitor, on the left, it has no charge. It's not hooked to a battery. It's just an inert piece of metal. Whether it's charged or uncharged, and we see it being charged on the right, the total charge is 0. So on the left, there's nothing special about it. It's just neutral material. On the right, you have positive Q and negative Q. And keep in mind that those added together, it's still a net charge of 0. So what's the difference between them? Well, the difference is the arrangement of the charges. Energy is stored in the arrangement of the charges. Energy is stored in the electric field. Now, how did the energy get there? And this goes back to the beginning of this chapter when I had 3 charges put in an equilateral triangle, and we talked about the work done to move them together. So work must be done to separate the charges. There's a very nice quote in the book, and I'll read it to you, and it's there on the screen. It says, "Burn gasoline or metabolize food, and you're rearranging charge distributions we call molecules into new configurations whose electric fields contain less energy." So even though in this chapter I'm mainly talking about capacitors, this is actually at the molecular level how we get energy from food, energy from gasoline, chemical potential energy. Now remember, for a capacitor, the potential energy of a capacitor is 1/2 CV squared. And I'll relate that to, if the voltage across the capacitor is Q over C, the charge divided by capacitance, we can replace that for V and get that the potential energy is Q squared over 2C. And here you see the electric field in there. Just to remind you, there's an electric field, and in the presence of these separated charges, work must be done to separate the charges. All right, going back up to the equation that I had at the 2 screens ago, potential energy is Q squared over 2C. Now, if it's a parallel plate capacitor, let's replace that C with epsilon naught times area divided by distance, and we get that the potential energy in a capacitor is the square of the charge on one of the plates times the distance divided by 2 epsilon naught area. Note that the electric field occupies the volume A times D. So imagine this cubic volume, the area times the distance. So the electric field, think of it as in a volume. So then we can talk about the energy density, which is actually joules divided by cubic meters. So we're going to take this formula, or actually we're going to take U over A times D, U over the volume, and we're going to replace U with this formula up top, Q squared D over 2 epsilon naught A. And it simplifies to the energy density is Q squared over 2 epsilon naught A squared. Now, back in section 23.2, we learned that energy is Q over epsilon naught A. And then we can say Q is epsilon naught A times, I'm sorry, I said energy, I misspoke. That's electric field. Electric field E is Q over epsilon naught A. So then let's solve that for Q, the charge, equals epsilon naught times the area times the electric field. And what this all boils down to is the energy density. So we need new letters here. We can't use the letter E. We're already overusing the letter E. So they use the lowercase letter U, and that's the notation I'll use. The energy density measured in joules per cubic meter. How much energy can be stored there in that electric field of some volume is 1/2 epsilon naught times E squared. So the energy density is related to the electric field squared. Notice that there's no other variables involved. 1/2 and epsilon naught are constants. The energy density is completely related to the electric field. Let's look at an example in the book, example 23.4. I haven't written it, but it says, typical electric fields in thunderstorms average around 10 to the 5th volts per meter. Consider a cylindrical thundercloud with height 10 kilometers and diameter 20 kilometers, and assume a uniform electric field of 10 to the 5th volts per meter. Find the electric energy contained in this cloud. How much energy is in that cloud? There, I've drawn it. We're assuming a nice cylinder, radius of 10 to the 4th meters, height of 10 to the 4th meters, electric field of 10 to the 5th volts per meter. So the total energy, and I'm using capital letter U, don't mistake that with the energy density lowercase u, but capital U, the total energy, is the energy density times volume. So remember, energy density is energy per volume. We multiply that times the volume, and that gives the total energy. Well, let's make some substitutions in here. Energy density is 1/2 epsilon naught times the electric field squared times the volume of our cylinder, pi r squared times h. Plug all those values in, we get 1.39 times 10 to the 11th joules, or 140 gigajoules. Compare that with gasoline, typical amounts of energy that we get from gasoline, or rather, how much gasoline would it take to give us that much energy? Well, in Appendix C in the book, it gives a variety of sources of energy. In gasoline, it says you get 44 megajoules of energy, of chemical potential energy, stored in every kilogram of gasoline. Well, to see how much gasoline it would take to get that much energy that's in this thundercloud, we have 1.39 times 10 to the 11th joules. That's what we got the answer. And then let's divide by 44 times 10 to the 6th joules per kilogram of gasoline. And that's 3159 kilograms of gasoline, or 6951 pounds, so more than 3 tons of gasoline. You can think that's 1160 gallons of gasoline. 1160 gallons of gasoline would provide as much energy as what's in this thundercloud. Now, what about a non-uniform electric field? For example, the electric field that emanates from a point charge, such as you see in this picture? Well, let's use small volumes, dV, so that the electric field is essentially uniform in each little volume element. So calculus we're going to use. So we can talk about a little bit of energy, little du, or du, equals the density times dV, which is 1/2 epsilon naught times electric field squared times dV. And the total energy in the electric field is the integral of all the little du's. So it's going to be 1/2 epsilon naught, that can get thrown out to the left, and we're left inside the integral with the integral of E squared dV. And this represents the stored energy, and therefore the work done to assemble the charges that result in the electric field. Well, let's actually do a problem involving that. Let's look at number 61 in the back of the chapter. It says a sphere of radius r carries total charge Q distributed uniformly over its surface. Show that the energy stored in its electric field is U equals kq squared over 2r. Okay, so it's a kind of physics problem I like, where it's telling us the answer. We just have to arrive at it. Show that U equals kq squared over 2r. There's my sphere of radius r. The electric field emanates from the surface. And we'll do the equation that I showed on the previous screen, that U equals 1/2 epsilon naught times the integral of E squared dV. Now, what we're going to do is make a substitution for dV. Now, here I've drawn in green a thin shell, and this thin shell has some volume dV. Now, what is its volume? And I'm not talking about the volume that's contained in the shell. It's a thin shell, but it has some little tiny thickness to it. And what's its volume? Well, it is the surface area of the shell times its little tiny thickness. So the surface area is 4 pi r squared times its thickness, which is dr. It's very thin thickness. And remember that the electric field from a point charge is kq over r squared. And as we've seen in a previous lesson, that the electric field from a sphere, from the outside of the sphere, is the same as if it were coming from a point charge. Of whatever charge is distributed on the sphere, it's going to be the same thing. So we make all these substitutions, and we'll now say that the potential energy, or the energy, is 1/2 epsilon naught. That's been thrown out to the left of the integral. And we make all these substitutions where E is kq over r squared, and then we have 4 pi r squared dr, so we have all this right here. Now, I'm also going to throw in here that there is K, and there's also an epsilon naught. And this is unnecessary to use both epsilon naught or K. We're going to use one or the other. And while epsilon naught is the preferred variable, you notice that the question says to show that energy is something related to K. So we're going to get rid of epsilon naught, put in terms of K. So epsilon naught is 1 over 4 pi k. And remember, that comes from that k is 1 over 4 pi epsilon naught. So whenever I see epsilon naught, it's only that one place outside the integral. I'm going to replace it with 1 over 4 pi k. So we do that. Any constants we factor to the outside of the integral, k squared, q squared, 4 pi, throw those to the outside. All that's left inside the integral is r to the negative 2 dr. Consolidate all of these constants. Some k's divide out, pi's divide out, 4's divide out, all kinds of things divide out. And what we're left with is kq squared over 2. And then taking the integral, negative 1 over r, integrated from where the sphere starts, the surface of the sphere, out forever, across the universe. So we're integrating over dr from the low end limit is r, capital R, the radius of the sphere, and the high end is infinity. And so doing that, I've brought the negative sign in this final line on the page. I've brought the negative sign far out to the left, and we have 1 over infinity, which is 0, minus 1 over r. And in the end, we get kq squared over 2r, and that's what the problem said to solve for. Let's do problem number 63, a little bit simpler than the previous problem. 2 widely separated 4 millimeter diameter water drops each carry 15 nanocoulombs. Assuming all charge resides on the drop surfaces, find the change in electrostatic potential energy if they're brought together to form a single spherical drop. All right, so there they are. Each one of them, it says, has a diameter of 4 millimeters. We'll say that's a radius of 2 millimeters. And they're going to join together into one larger sphere. From problem number 61, the previous problem, we found that the energy, the total energy of the electric field coming from a sphere is kq squared over 2r. Well, we know k, we know q in this problem, 15 nanocoulombs squared. That's for one drop. Divided by 2, divided by the radius, 2 times negative 3 meters. This will give you what that fraction there is, the energy in one drop. And then we're going to multiply by 2 because there's 2 of them. And if you go through the calculation, you find that the total energy that is present right there is 1.01 times 10 to the negative 3 joules. And that's the energy when they are far apart. Now, we're going to bring them together. Remember, the question is asking, find the change in electrostatic potential energy. All right. The total volume, when you bring them together, each of them individually had a volume of 4/3 pi r cubed, and we're going to multiply times 2, so that becomes 8/3 pi r cubed. So that is the volume of the total volume, and that's the total volume of our new sphere. But I want to know the radius of our new sphere. So now let's imagine we're bringing them together, and let's find the radius of the new sphere. Volume of any sphere is 4/3 pi r cubed. And so we can say 4/3 pi r cubed, the new volume of the bigger sphere with the capital R, is 8/3 pi times the little radius cubed. And we're just going to figure out how big the new radius is. So simplifying things, the pi's, the 1/3 go away, and we're left with big R cubed is 2 times little r cubed, which means that the radius of the bigger water droplet is the cube root of 2 times the smaller radius. So these two spheres, equal spheres, when they came together to make one big sphere, it's not a sphere that's twice as big. It's actually, well, it's twice as big in volume, but in terms of diameter or radius, it's only 1.260 times the radius. So now let's apply that new radius to our new sphere and find out what the new energy is. Energy is K times, now we have 2Q because it's twice the charge of each of those individual Q's that we had before, squared, divided by 2 times the big R. And as we plug in the values, there's K, there's your total charge, 30 nanocoulombs squared, divided by 2, and now your big R, and you get 1.605 times 10 to the negative 3 joules. So it changed just a little bit. The new potential energy, or the new energy, is 1.605 times 10 to the negative 3 joules. The old one, solved for on the previous page, was 1.01 times 10 to the negative 3 joules. So in bringing them together, it actually gained in potential energy. And you can think, that makes sense because it took work to bring them together. Remember, they were both positively charged. If they come together, they were repellent to each other. So if they came together, it took a little work to get them together, and that work is shown in the increase in potential energy. And that is the end of chapter 23. Have a great day.